Hello, this is POGO 511, Introductory Data Analysis for Policy and Government. This is video 10, Standard Deviation. Please take a moment to connect with the outcomes as a result of watching this video. We will review many different concepts today, so I highly recommend having your textbook available to you because we're going to reference one of the appendix references. And feel free to watch this video over 2 sittings because we are going to go into some detail with some of the concepts that are reviewed and found on this slide. So big picture, inferential statistics are utilized by researchers to draw conclusions about a population from a sample. So we know that it's unreasonable and impossible to collect data from every subject or every individual within a target population. We just don't have the resources and the time, and we can't have assurances that every single person would participate. So to work around that, researchers will implement different techniques to collect data from a sample to make conclusions about a population. So please keep in mind that in order to determine a sample, you have to utilize different types of criteria and different types of techniques to make sure that that sample is representative of the population, because it would be a really bad situation if your sample isn't representative of the population when ultimately you're going to be drawing conclusions from that sample about the population. So before you can even engage in any of these data collection strategies or statistical techniques about that sample, you need to make sure that you've done your due diligence to ensure that the sample you are inviting feedback from is truly representative of the population. So as I mentioned, there are some techniques that researchers will utilize about the sample and in their data to draw conclusions, and we're going to review those today. So what? In terms of the importance of this type of work in research, researchers want to draw judgments about the distribution of the sample relative to the mean, and to determine if it's normally distributed and where outliers, if any, may exist in the data. That really drives the reason for implementing all of the items that are found within the center of the slide here. So you want to draw judgments about the sample, and you do that by first considering the population versus sample, determining if the data are normally distributed, utilizing something called confidence intervals and z-scores and standard deviation, which we'll review more closely in a few slides, and to identify outliers. So before you can draw judgments about the distribution, you need to be able to implement these different techniques within research. By doing those things collectively, you're able to identify outliers and make generalizations about a population from that sample. So let's begin with the major difference between population and sample. As I mentioned in my earlier remarks, it's impossible to collect data from a target population, which would be the entire set of subjects of interest. Rather, researchers will take a sample, which is a subset of the target population, and invite feedback from them. So while we've identified maybe about 20 people here within the target population, we've selected these 4, 1, 2, 3, 4, to be representative of that population and will constitute our sample. Here's another example. Let's pretend that the school board and superintendent want to ask parents about their preferences for their child's learning. Are they interested in having their child participate in learning virtually in an online environment or in person? It's impossible to collect data from all of the target population, in this case 6,200 or so parents. Instead, they'll select 250 parents randomly to constitute their sample. This is an example of a sample versus population. So standard deviation describes the calculation that shows the distance between an individual observation from the mean. So the mean, which is graphically displayed here with the X and the line above it, that's how researchers will refer to the mean. You basically want to say, if this is the mean, if this is the average of scores across a full distribution, where is this score, where my red cursor is? I hope you can see my red cursor. I might need to change it to a different color just so you can see it a little bit better. There we go. If here's my data point, where is this data point relative to the mean, to the line? Or if a data point is over here, where my white cursor is, where is this data point relative to the mean? That can be calculated by utilizing the standard deviation statistical technique. If the standard deviation is larger, that means the data are more dispersed, farther from the mean in both directions. If the standard deviation is smaller, that means the data are closer to the mean and similar in value. So you might be wondering, well, what does it mean to be normally distributed? This is a graphical representation of a normally distributed set of data. Let me just change the color again. All right, so what you have here is your data represented in this normal curve. And this refers, when we're talking about normal distribution, refers to the distribution of a variable that resembles a bell-shaped curve. In essence, the left and right sides of the curve mirror each other. So when your data are normally distributed, you can say that 68% of the observations, so thinking back to that school example, when you think about 68% of 250 parents, their data will fall within one standard deviation of the mean. There we go. 68% of the data will fall within one standard deviation of the mean. You can also say in a normally distributed data set that 95% of the observations will lie within two standard deviations of the mean. So here's your mean, which is represented by 0 here. You can say that 95% of the data in a normally distributed data set will fall within two standard deviations of the mean. And this x-axis here shows the standard deviations. When you think about 99% of your observations falling within some distance of the mean, you would say that 99.7% of observations will lie within 3 standard deviations of the mean. So this is how you can describe a normally distributed data set, both in words here, which are on the left-hand side, as well as a visual display here on the right. Confidence intervals are also a really helpful tool when you're trying to think about the distribution of data, and you're thinking about it through the lens of, this is a sample. I want to have assurances that the distribution of these scores would be what we would find if we were to do this same study with the entire targeted population. So what researchers will do is say that the population mean lies somewhere between the lower and upper end of a confidence interval. And I like to think about this like as a range, as we talked about in the video prior to this one. Like, what is the range of the scores? So the range of the data that would be collected from this sample could be a confidence interval set at 95% or 99%. So if you were to set your confidence interval at 95%, you're basically telling your audience, you're telling your stakeholders that 95% of the time, the mean will lie within this confidence interval. And what I've done on slides 11 and 12, I'm just going to skip z-scores for just a second. On slides 11 and 12 here is show you a visual representation of what this confidence interval could look like. So the confidence interval, CI, is set at 95%. And it has a corresponding z-score of 1.96 on the plus side here, and then negative. So that means that all of your data points, all in here, capture 95% of the possibility of where a mean score could fall in a normally distributed set of data. If you set your confidence interval at 99%, that visual depiction is here. with a corresponding z-score of plus or minus 2.58. That means that 99% of the times the mean will lie within this confidence interval of 99%. So I'm just going to scoot back to that slide on z-scores and give you a moment just to read through the content on this slide. Please take a moment to read the information found here. So I'm going to slide back in and walk through some of the content with you. So a z-score is the number of standard deviations that one data point is from the mean. So if you think about this, the z-score of 1.96 basically means that this data point right here has a standard deviation of 1.96 from the mean. Okay. So z-scores are really helpful when you're thinking about confidence intervals and describe the number of standard deviations that one data point is from the mean. So if you were to invite feedback from those 250 parents, where might their feedback lie on this curve? And how many standard deviations is that specific data point from the mean? That's where z-scores are really helpful. So as I mentioned in the previous video, you certainly have to be careful when collecting data on a continuous scale, such as salary information, household income. I even think about like weight, weight that folks may have. All of those would be examples of things that you need to be really mindful of when representing the mean score. It could be highly misrepresentative to look at personal income of your entry-level staff and the CEO. If you were to look at the mean score in that example, it may not be representative of the majority of staff within that organization. Standard deviations can be used to detect outliers, which are values that are unusually small or large among the values within a distribution. So an example of an outlier here would be a data point that may find itself all the way here, where my red pointer is. It's not within the normal distribution. You also could find an outlier over here. So I think it's just important in that example, if a CEO's salary is $2.5 million and your entry-level staff person is making $40,000, their scores are way different than likely what the average is within an organization. So as you move forward, I'd like to invite you to think about which data may be collected by the program that you're interested in exploring, and which variables could be really interesting to look at through the lens of standard deviation and confidence intervals. We'll certainly spend some time in class going through some more examples, but I want you to begin thinking about data that could be collected or is already collected with the program that you're interested in, and see which of those data might be a good fit for analyzing through the methods that were described within this video. Thanks so much for watching, and please connect with me during office hours if you have any questions.